Okay, so now let's talk about our second example. So in the previous example, it's somewhat a production problem, right? We need to decide what products to produce. But in many situations that when we are making decisions, we also need to consider the future. Okay? So let's discuss these multi-period problems in which we need to produce and store. So in many cases, products produced today may be stored and sold in the future. And the reason to do that may be varies. So for example, maybe the daily capacity is not enough. You expect that in the next week is a Valentine's Day. So today you need to produce a lot because you cannot produce everything on the Valentine's Day to fulfill all the demands there. Okay? Or maybe production is cheaper today, or maybe the price is higher in the future, okay? Because costs and the prices, they may fluctuate. So there may be these reasons to produce today, but sell them in the future. When we are making these production decisions, now there is another dimension of decisions that we need to take into consideration. That's the inventory decision, right? When you have this option about storing products, if you do not use it, then this decision typically is not optimal. So if you really want to save as most money as possible or earn as many money as possible, you may need to consider all the options. And here, let's discuss these two options. Suppose the problem is the following. We produce and sell one single product. For the coming 4 days, okay, here you may interpret them as weeks or months or whatever, periods, okay, let's call it days. Your marketing manager has promised to fulfill the following demands. For each of these 4 days, you need to ship 100, 150, 200, or 170 units of your product to your consumers. Okay, you need to have this amount of products at hand. The unit production costs are different for different days. Okay, today is the cheapest, and tomorrow is the most expensive. For all the 4 days, is the unit production costs are $9, $12, $10, and $12. So you have a strong incentive to make production today, right? If you can make all the productions today and then sell them in the future, then it will be cheaper instead of making all the products on that day when you need them. And also you know that the prices are fixed. So if you want to maximize your profit, all you need to do is to minimize your cost. Okay? That's something you are expecting. So we have the option to store products, but there's one thing that we need to keep in mind. When we are storing products, we incur some inventory cost. For example, here in this problem, we assume that when you store a product for a day, you need to pay $1 as a cost. Okay? I encourage you to think about this situation about inventory cost. Why do we have inventory cost? When we make one product and put that product in your warehouse, where do you pay this $1? Okay? Think about that and think about how may we measure this amount of inventory cost. Okay, I ask this question here is because, for example, for production cost, you know why you pay production cost. You pay that to the material supplier, you pay that to your workers. But for inventory cost, where do we pay this $1? Okay, that's my question, and think about that. Anyway, suppose this has been determined, and take that into consideration. Suppose I produce everything today to fulfill all the demands. The total cost I may need to pay is the following. I have 9 times 620. That's for the production cost. And today, okay. and then I need to pay $1 for 150 units, okay? Because this amount of product has been put in my warehouse for 1 day. And for 200 units, they must be kept in my warehouse for 2 days. For the remaining, they are here for 3 days, so the inventory cost is $3 per item. Okay, so in total, this is the total cost. And my goal is to minimize the total cost. Okay, I also need to tell you about the timing, what's happening in each day. In each day, first you go to your warehouse and see that you have some beginning inventory that are leftovers from the previous day. And then you make your production to get new products getting into the inventory pool. And then you sell them. Okay, you sell your products or you fulfill your demands. And finally, you get your ending inventory at the end of this day. Okay, so in each day, you have an equality. Your beginning inventory plus your production quantity minus the amount you sell will become your ending inventory. Okay, and inventory cost, we assume that it is calculated according to the ending inventory, according to how many items you have in your warehouse at the end of each day. You calculate the inventory cost. So certainly that these are some kind of approximation, but anyway, that's the way we measure inventory cost. Okay. One additional thing is that in each day, you may produce everything you need for that day. Okay. You have the option to ignore inventory. Okay. You may just produce and then sell because production occurs before sales. If you first sell and then produce, then that's a different story. But anyway, yeah, let's consider this situation here. Okay, so let's make a definition and then do the formulation. What I want to know is about for each day, how much should I produce, right? And also I need to know for each day, what's my ending inventory because I am making production and inventory decisions. Okay, so I'm making production and the inventory decision for XT and YT. Here, I need to make sure that you see this term ending. Okay, we're talking about ending inventory instead of beginning inventory or average inventory or whatever. If you are doing this problem, you cannot write YT equals inventory of day T. That's not precise, right? At least you know there are ending inventory and beginning inventory. If you want to make a clear definition, you need to say it is an ending inventory or whatever. That will also changes your formulation accordingly. Okay? Here, I emphasize that we are talking about ending inventory. And my objective function would be the following. Given these numbers, I want to minimize the sum of production cost and the sum of inventory cost. This is my objective function. Now I need to keep an eye on my inventory because there must be some connections between production and inventory, right? In the first day, I have nothing at the beginning. I need to make some production and then to pay for to deliver the 100 units of demand. Then I get my ending inventory. Using this ending inventory, I then make production to fulfill the second demand and get the second inventory and so on and so on and so on. So what constraint do I have? For day 1, I have this. X1 minus 100 must be Y1. For day 2, initially I have Y1. Y1 is the ending inventory of period 1, which is exactly the beginning inventory of day 2. So Y1 plus X2 minus 150 will become Y2. The amount I have at the beginning plus the amount I add minus the amount I sell give me the ending inventory I have. So in total, I have 4 constraints regarding this equality. And these are typically called inventory balancing constraints. okay, for these kind of inventory problems. Inventory must be balanced across different periods. These Y variables are connecting different periods because for period 1 to period 2, ending inventory of day 1 is the beginning inventory of day 2. We also need to fulfill all the demands, right? We cannot choose to produce nothing. That's not allowed. So x1 must be non-negative. X1 must be greater than 100. And then y2 plus x2, the amount I have plus the amount I add into, must be enough to fulfill those 150 demands. Okay? And so on and so on. And also production and inventory quantities cannot be negative. Okay, so this is my complete formulation. I need to minimize the total cost subject to 8 functional constraints and 8 non-negativity constraints. These are the inventory balancing constraints, and these are the demand fulfillment constraints. Okay, these are my non-negativity constraints. By writing something like this is my complete formulation, and I expect you to also write your formulation in this way. One question here I want to discuss is that actually we may simplify this formulation. By looking at these constraints again, we realize some things, right? Some constraints are not really required. It's very often that your first draft of your formulation is not either is not correct or is not perfect. There are some constraints that are actually redundant, and here let me give you this example. So we're talking about inventory balancing, and also inventories cannot be negative. So together, actually the demand fulfillment constraints are not required. Okay? For example, day 1. If you have x1 minus 100 is y1, and y1 is non-negative, then together you know x1 must be at least 100. This constraint is redundant. And similarly, all these 3 constraints are redundant, so the formulation can just be this one. Okay? You can ignore the 4 demand fulfillment constraints. So in many cases, after you formulate your first program, it will be better to look at it again to see whether something can be removed or something can be reorganized so that you may get a better formulation. That's also something similar to the process of writing programs, right? First, you try hard to find a good program, and then you try some more works to make it a better computer program. Here is the same thing. You find a correct linear program, and then you make it better. This one and this one, both of them are correct, but this one is better because you removed those redundant constraints. Okay, finally, I want to mention something about personnel scheduling. There is a story on the textbook about United Airlines, which is one of the largest airlines in the United States and also in the world. Okay, United Airlines have the following questions regarding personnel scheduling. Okay, in an airport, think about this situation. You have counters in airports, right? You need to schedule a lot of people there. And also you need to have other workers working on, for example, those delivers or check-ins or luggages or other services. Okay, you need to have a lot of workers at each airport, and the amount you need is different for different time periods. So suppose you have this schedule. You know, for some time you do not need so many workers. But for some other peak periods, you really need a lot of workers. However, persons work for 8 hours continuously in each day. Even though you may ask them to arrive the airport at different time. For example, 10 people may start to work in this shift, or 10 people may start to work in this shift. People may start differently. but all of them work for 8 hours continuously, right? So it's not very simple to think about how many people do I need to fulfill these requirements. Okay, for example, I need 10 people from 6 to 8. I need 15 people from 8 to 10. If I hire too many people, if for those peak demand periods I hire too many people, they will also work during other periods, right? And then I am wasting some human resources. So if I want to somehow save some money regarding hiring people, then I need to plan for it carefully. Okay? So the story is that linear programming is used by United Airlines to save $6 million in each year, simply for finding a better schedule for workers. Okay? If you do not use this kind of scientific way, if you use only experience or intuitions regarding how to schedule people at different shifts, then probably you cannot find a very good or very efficient solution. But with linear programming, you are able to get a much better solution, and that can save you really a lot of money. Okay, read that story either in the textbook or in the article.